Yeah, so I'd like to give just a shortened version of the talk we gave that Bill Kane and I gave together jointly at the Investors Day, really focusing on technology trends, not to be a focus on a specific product roadmap or specific technology roadmap for HDST, but trends in the industry, how that was supporting our products, our core, our opportunity, and what opportunities for growth there were that we saw as we saw the evolution of trends come out. And again, I think this is important for investors, for analysts, and for our employees to try and understand. But to start, Mike's really alluded to a lot. It's really a time of change right now. Personal devices, smartphones, tablets are taking function away from PCs today, same as PCs took functions away from mainframes 20 years ago. Mainframes didn't go away, but we started to get productivity and other things. The same thing is going to happen. Storage trends change. Back in the mid-80s, probably almost 100% of our storage was in the enterprise on big 14-inch diameter disks. The PCs changed that. Now, over 70% of our storage is on client devices. As we migrate forward, we're going to see drivers of change. Mike talked about the cloud. Clients are sort of getting big enough, storage growth there, other things happening. But where's the big growth in the cloud? We're all going to access the data. We're all going to be connected where we are. So there's changing happening where the data growth and what the data factors. We're actually going to see shift back into the data center. And perhaps by the end of this decade, 40% of all our storage will be back in the data centers and back in the cloud. Customer requirements, Google, Facebook, Amazon Web Services. They're now end users. They're building their own applications or systems and operating them. They're much more willing to partner, much more willing to understand their application, and much more willing to differentiate solutions and work with us to make those solutions happen. And we see slowdown in aerial density as we're coming to the end of PMR technology. Aerial densities that 10 years ago were at 100%, or we've commonly seen 45, 50, 60% growth rates in aerial densities, are slowing down. That's going to change some of the dynamics of how things change for us. So change is difficult. Change causes doubt, causes uncertainty, causes people to write it's the end of HDD. In 5 years all HDDs will go away. But it's also an opportunity for change. And if we see that as the world changes and new things come, there are no incumbents. And if we are a leader, we see those opportunities, we take those opportunities, there's great opportunity for growth. Rather than being frightened by change, we should embrace change as we go forward. And to do that, though, we need to move fast. We need to be dynamic. We need to stay ahead of the curve, rather than being swallowed up by the wave. We need to be surfing on the leading edge of it. We need to focus on broadening and differentiating our products. We need to expand our capabilities as we go into new segments and new markets as the opportunities evolve. And we need to lead. We need to be the technology leaders as we go forward. Because it's all going to be about tiering of technologies and how we mix technologies. The biggest thing that investors ask about is, aren't SSDs going to replace HDD? And the answer is no. We're going to see tiers. We always have seen tiers. We'll continue to see tiers of storage. The classic model is this triangle or pyramid. The technologies at the top are the fastest technologies, but the most expensive technologies. As you go down in technology list, you see technologies that are slower but much more cost-effective dollar per gigabyte. Typical applications balance the amount of capacity at each one of these levels based upon the overall cost, and then manage data up into the higher tiers here to get the performance when they need it. So it's about building a balanced system, building the various tiers, and typically each tier there's been 10 times as much capacity in the tier below it than in the tier above it. And get managed out. Now, a couple of comments. Some people say, well, SSD and HDD both end in D, therefore they must be in the same tier. They must compete and one has to win. No, I'll go show in a second. There really are separate tiers, and we believe they're going to remain separate tiers to go forward. The other thing that people say, oh yeah, that's a nice picture, but that's the old data center picture. We're now in the new world. We've all got smartphones, and we don't have any of this stuff. We've just got flash in our smartphone. And I ask, when you downloaded all of your songs off of iTunes, where'd they come from? An HDD. When you backed up and signed up for auto backup and it went to the iCloud, where'd it go to? An HDD. When you went to surf to find out what the weather report was before, where did you get the data from? An HDD. There's tiering in everything we do. It's just we may not see it in the same rack, we may not see it in the same data center, we may not see it physically connected, but all data is tiered because of the cost effectiveness of each layer. So let's get specific about that though. Let me go into give you a plot. I'm going to show the x-axis here is going to be cost. It's capacity per dollar is the bit cost. So to the right over here is the lowest cost. I'm going to put performance on the y-axis, the highest performance at the top. Can anyone guess? It's like the Verizon commercial. Anyone guess where you want to be? You want to be in the top right corner, the cheapest and fastest as possible. Well, I go back 15 years ago and normalize to SRAM, cost and SRAM performance, DRAM, HDD, and tape. This is what it would look like. And what you see is there's no technology, there's no single technology up in the top right corner. It's a diagonal line of technologies here. It has a slope of about every time you want a 100x increase in performance, you got to pay 10x higher in dollar per gigabyte to get that. So I build systems that tier these together that have a little bit of SRAM, a little bit more DRAM, a lot more HDD, and historically a lot more tape back here for archive and backup to make that solution. Now, what has happened over this, that's 15 years ago, and oh, by the way, point out, life used to be simple back then because I had two technologies which were volatile, wouldn't store the information, I called those memory. And I had two technologies down here which were non-volatile, which I called storage. As I show as we go forward, those lines and those distinctions start to get blurred. But as I go forward in time, density growth rates change, performance growth rate change, and I fast forward here and you can see what happened. The biggest change you see is that HDD and tape drop way down here on the performance gap. In doing that, a very large gap of performance opened up between DRAM and HDD. And that's because HDD and tape are mechanical devices and their performance did not scale as semiconductor lithography and other advancements happened. And because of that gap, what happened? We saw the advent of NAND flash come in and start to become significant. First SSD was 1991, 20 megabytes from SanDisk. SSD has been around a long, long time. They only became relevant and important when the HDD performance gap became large enough to make a hole there and make an opportunity for flash. But you see, it's following on the same diagonal line here of HDD DRAM. It's not down here competing on top of HDD. It's not up on copying DRAM. It's kind of more or less following the same thing. The one guy who's actually fallen off a little bit out of the diagonal is tape. We'll come back and talk to a little bit more of that and where we think that means going forward. But that's where we are today. Then people say, oh yeah, but flash is reducing so fast in price, pretty soon turn around tomorrow and be on top of HDD and it'll wipe out HDD, and that's only a temporary tier there. Let's go and look at that for a second. HDD based upon magnetic recording, SSD today based upon NAND flash. Both operate in a simple principle. I get a capacity which is proportional to a surface area times the density, data density on that surface area. One generation to the next, that surface area roughly stays the same size. The cost of making that surface area roughly stays the same size. And so as the density goes up, the capacity goes up, and if I can sell it for the same price I did before, my dollar per gigabyte drops and I get a better solution. Both scale roughly the same way. What's the difference? In the case of HDD, that surface is this disk. Relatively speaking, that's a very inexpensive disk. It comes flying out of the sputter tool every 10 seconds. It's very cheap. The high density, which is where all the cost goes into, is done in a single element on the recording head. And then I sweep that recording head across the full surface through mechanical access by rotating the disk and moving the actuator. So I only have to put the fine lithography into one head. If I actually go look, I make those on a wafer. So on a 200 millimeter wafer, I can make 80,000 sliders, and this one lithography, which takes the challenge, can store up to 40,000 terabytes off one head wafer. When I go over to NAND, I have to do the fine lithography and density over the full surface area. I don't get to make a cheap surface one data point. I got to make all the density here. So that makes it a much more expensive wafer, and it only produces 2 terabytes at the equivalent point in time. Now, what it does give me, because it's interconnected on the wafer, I get all the wiring, and therefore I switch things very fast through electrical wires and leads and transistors rather than having to mechanically move something. And I can also break these up into a small number of dies and connect them in parallel behind a controller and get high throughput through parallelism, accessing multiple chips in parallel, much like striping a drive. So the net is, when I produce an HDD over here, the relative cost in dollar per gigabyte versus SSD is about 10 times cheaper. That cost is really coming from this mechanical advantage, but it's at a bench level, an SSD typically is about 100 times faster because of the parallelism and because of the interconnects. Well, where is that? It leaves us at 10x today. Where is it going forward? Well, again, surface areas aren't going to change much. It all has to do with how the relative density, growth rates and densities are going to change in those two technologies as we go forward. So let's take a look at that. Let's first look at historically. We'll look at NAND, we'll look at HDD, we'll look at tape. If we look at HDD, we all know that the growth rate in areal density has varied significantly, but over the last 13 years, it's averaged roughly around 41%. That's the question, what has NAND density growth rate been over the last 13 years? Interestingly enough, you see two very parallel lines, about 41%. So they've both been scaling roughly the same growth rate on average. The one technology actually which is a bit troubled down here is tape, which is growing at 28%. And so why you see that the gap of HDD and the cost and the relative dollar per gigabyte of HDD approaching tape is because tape has not been growing as fast. Well, that's historical. What about we go forward? We all know we have challenges in HDD, and we certainly do. Areal density slowing down as we come to the end of perpendicular magnetic recording. We're looking at technologies to extend that a little further with shingled magnetic recording. We're looking to come up with new inventions to continue to push that out farther with hammer. And then combined with even more breakthrough ideas, a hammer with good pattern media and two-dimensional magnetic recording, all kind of combined together. But we have a roadmap. As an industry, we believe that roadmap will support about 20 to 25% compound growth rate in areal density. At the high end of that range, if we are to succeed at developing these technologies, introducing them rapidly into product, and on the low end of that range, obviously we have difficulties or are not successful bringing those in. 20 to 25% for HDD. What about NAND? Well, NAND has similar challenges in the stage of its technology. The last time we're going to see a planar floating gate is going to be 20 nanometer, which is shipping today. The next step in 15 or 16 nanometers, they have to go to two-dimensional gates or various other trapping technologies to store the electrons because the number of electrons on the gate is becoming too small. As they go beyond that to continue growth rates, they need to go to three-dimensional stacking and layering these things up, and eventually they're going to go out and continue on this roadmap before the end of the decade. We'll have to see cross-point, three-dimensional arrays to things like resistive RAM or some other new invention technology. To support this kind of roadmap, people are looking at and projecting within the semiconductor industry 25 to 30% growth rate in areal density. So very similar between these. So we do not think based upon the projected density growth rates we're going to see a substantial change in that ratio of 10 to 15x difference between NAND and SSD. So we think HDD and NAND flash will continue as independent tiers as we go out in time. But let's go back to this graph and really talk about not only these tiers that are going to be built together, but where are the opportunities that we see from looking at this graph? First, we can look down the bottom corner down here at tape. We realize that HDD is encroaching upon tape because of the higher growth rate and density of HDD versus tape. We talk about cold storage opportunity, and that we could reduce the cost of HDD through various tricks, even 60% more compared to today. We'll start to overtake a lot of tape applications. We'll start to introduce applications for brand new data sources. Data today which is being thrown away because it's too expensive to keep. Data that, the biggest example that people often understand is Facebook. Facebook keeps high resolution pictures, not the full resolution, have high resolution, but they'll keep some reasonable resolution. But over time, they start to only save down-resing those to lower and lower because they can't afford to save all that information. If we can produce very low cost, they can. Facebook does not use tape. And tape would certainly not be usable for someone to go out and do a search and want to click on a picture and wait for a tape library to load it up. The other opportunity to talk about flash. Flash is still evolving. Flash is growing. This segment is just opening up. We're just figuring out how to use flash. We're starting to utilize flash, figure out how to get the performance advantage and offset the cost disadvantage of it. We'll see opportunities in hybrid. We've heard a lot of discussion of hybrid drives, really combining in between the flash and HDD. On the higher performance end of this will be PCIe. How do I go to even higher performance? But today, our biggest opportunity we've taken advantage of in HGST is looking at SSDs with SAS and fiber channel. We are the market leader in SAS and fiber channel enterprise class 8 SSDs today. I don't know how many people knew that. We're the market leader in this segment in here in the main, and we're developing and have a program to go develop an even faster, higher performance SSDs to sit on the PCIe bus, where I'm going to eliminate the serial interface here and go to parallel interface. And if we look even farther than 5 years out, which of these technologies then is most challenged? Is it HDD? No. The most challenged technology is actually DRAM up here. DRAM has a very large trench to get its capacitance. Scaling that and going to further smaller linear lithography steps is very challenged. So most of the memory companies are looking at new technologies to potentially replace DRAM. Two examples are phase change memory and magnetic RAM are the most favored today, the most mature technologies out there. The other interesting thing about them is these are both non-volatile technologies. So now, not only are we introduce flash here, which is non-volatile, but the whole discussion of what is memory and storage and what's volatile and non-volatile is starting to blur. We'll see many new opportunities. For example, we love to have replaced the DRAM today that we put on an HDD with MRAM, so now my buffer not only becomes fast, but it becomes non-volatile, and all the new applications that can happen there. So, but let me go through a few of these opportunities down here. I'll start down here on cost side. Let me talk about cost. The biggest pain point always in a data center, any of our customers, is I want lower cost. I need lower dollar per gigabyte, I need more storage, but I need it cheaper. Well, what do I want to do? I want to actually go back and build a bigger capacity drive at lower cost. How do I make bigger capacities? Well, it's fairly straightforward. Surface area times density. So if we're given density, I have more surface area. So I got the biggest diameter disk I can get. Today that's 3.5. Then I try and put as many of those platters together to get even more surface area as possible. And HGST pioneered the 5-platter 3.5-inch disk. Of course, I don't want to necessarily spin that in the enterprise at 10,000, 15,000 RPM. I want to slow that down, get to go at 7,200 RPM or maybe 5,400 RPM to make that work. And everyone says, well, that's straightforward, that seems simple to do, and that's great, and that looks like a long roadmap. The real challenge, you understand, is there's a massive mechanical challenge in doing this that we substantially underappreciate in the industry. The tip of that disk is spinning about 80 miles an hour. It's about a millimeter away from a surface which is totally stationary. There's lots of vibration and turbulence and airflow that goes on in there, and how do I position and how do I continue to scale that? The example I use for many people to understand, you're driving your car at 80 miles an hour, and don't listen to the attorneys, I didn't tell them to drive 80 miles an hour. But imagine you were driving 80 miles an hour, put your arm out the window. It'd be bouncing all over the place, wouldn't it? You'd be really hard pressed to keep it stationary. You know that to be equivalent precision to the HDD, you would have to hold the tip of your finger perfectly still within 1/100th the diameter of your human hair. Almost impossible for us to imagine. But that's what we have to do across this HDD. And we have to do it very reliably with lots of design margin to get high reliability, because as I get very large drives, and I start putting large drives in there, they better be very reliable, or I'm going to be pulling all those drives out, replacing them, and customers complaining. So, who has the industry's only 4 terabyte, 200 million hour MTBF drive? HGST. So this is a tremendous product going after dollar per gigabyte capacity. But we got to continue to extend this. How do I deal with those mechanical problems? And by the way, what the other pain point in the data center is power. I don't spec a data center based upon square footage. I don't spec a data center based upon terabytes of storage. I don't spec it based upon MIPS. I don't spec it based upon the size of the I/O pipe going in. Data centers are spec'd today based upon megawatts of power they can pull off the grid and get in. Power is becoming the limiting factor to building and growing data centers. So, what have we done at HGST? Imagine I took that air that's inside the drive and replaced it with helium. Helium is 1/7 the density of air. So now all that shear that's going on by these disks spinning at 80 miles an hour in there suddenly is reduced substantially. So all that shear goes down, that power goes down, your miles per gallon in your car goes way up when you reduce and make it more streamlined. When I stick that arm outside the window now, the gas or the thing is hitting is 1/7 the density, a lot less force on it. I can hold my arm much more still, much better before. When I do this, I can now go from 5 platters to 7. I can solve the mechanical problem, put 7 platters inside, and I get a 23% reduction in power of this disk pack spinning. So when I combine that, I've got a 40% increase for more platters, so a 23% reduction. I get a 45% reduction in watts per terabyte. almost twice as much capacity I can now put in a data center which is constrained by power. Now, putting helium inside a drive is nothing new. I probably heard about the first few weeks when I started working for IBM on hard disk drives. What is the challenge? The challenge is, how do I keep it inside? And whenever I have a helium balloon, what happens? It all leaks out. Helium is a small molecule, it's very energetic, it tries to get out of everything. The challenge is, how do I seal it inside, keep it inside, guarantee I'm going to keep it inside, do it cost effectively, and be able to do it in mass production in the factory. And that's the innovation, that's the trick, that's the secret which HDST has to go deliver this product. So this is exciting. Talked about capacity, dollar per gigabyte, talked about power. The last major pain point in the data center is performance. How do we solve performance? We say SSD. SSD, we've got a tier in here, we've got to look at it, and for those who don't and haven't looked at NAND, you start to realize that the major problem with using NAND is it has this one problem. It's called endurance. I can only write information to a NAND cell so many times before it wears out. And in conventional consumer electronics, we're using something called MLC. It's really 2 bits per cell of information stored in there. Typically, I can only write that cell about 6,000 times. And for your camera, your cell phone, and other things, that's perfectly fine. Even for a SATA SSD, that can be fine. But in a write-intensive enterprise application, I wear that drive out in 3 months and I'll have to pull it out and throw it away. It doesn't work. So new technologies, new tiers, but more expensive tiers of NAND were developed called EMLC, Enterprise MLC, or the original single level cell, which is the highest performance, but highest cost, highest endurance. So I have to go build solutions, even tiering within this, just as we have 10,000, 15,000, 72 RPM drives, we have to tier the various NANDs in here, and we have to look at solutions which meet the requirements. So if it were simply a media streaming or boot server, mostly read application, I could use MLC. But really for most of the applications which we sell into, we have to go up and use at least EMLC, or up in even the highest performance SLC. And we keep trying to figure out how to use the cheaper technology and drag it up to have higher performance and high endurance by changing controller technology, signal processing, by doing over provisioning and product designs and many other tricks. The problem is that's kind of just keeping us treading water. Every time I shrink the lithography, every time I make that cell smaller, the number of electrons goes down, the endurance drops. So I'm chasing all these tricks over here just to keep flat. When the next level of NAND comes out and I get the cost advantage of a higher density, I'm going to have a big loss. I've got to bring all this technology just to keep floating. But if we go look at our products, our SAS fiber channel products in this segment, we offer both an EMLC version and an SLC version to go address both those markets and bring those products to bear. And again, leveraging our knowledge, experience in HDD with our sales and support and qualification, we're the market leader in SAS fiber channel. But we have a project going on to try and develop a product to go to PCIe. SAS is a serial interface. It's network switched out there. How do I get even faster? How do I get closer to the processor? I want to get on the PCIe, the parallel bus, which is directly connected to the processor. So off trying to go after the various highest performance end of the spectrum. So I showed you it's all about tiers. I showed you we have the highest end focused on, we've kind of got SSD, we've got HDD. We're expanding to try and go even farther in SSD up to PCIe. We're trying to expand even more to go down cold storage, and with the Helium technology go even lower dollar per gigabyte in power. The next challenge I'm going to execute that is, how do I manage all the data among all these devices? How do I build hardware and software solutions to help people make it easier to get the data in the right place so they can get the optimal solution to manage the data where it needs to be? Who's better able to do that than the person designing and building those technologies? So again, as we continue to expand out in the products, we also need to look at the overall solutions and how do we expand and use our knowledge to build better solutions in between it. So those are great opportunities for us. I'm really out of time here in terms of going that, and we've got to come back and look at that and address. But those are where we are, what we're trying to build on, what we're trying to expand into, and where we need to look to the next step beyond. So I'll just come back. Times are changing, but those are fantastic opportunities for us as a technology products company, technology solution company, to build better solutions, to look at expanding our value beyond HDD, how do I expand the SSD, how do I expand it further, how do I build solutions, how to build software, how do I get software drivers to accelerate these things, how do I marry hybrid things together,
We need not to be frightened of change. We need to embrace it. But we need to be fast. We need to be nimble. We need to be innovative. And we can't be afraid of change. As I say, if we're going to change those from words into actions, we need all of our employees and all of you to understand that, to buy into that, and participate in this change, to protect our core, to grow our core, but also to expand our business beyond that. So, thank you.